Are we going? I can never tell what's happening, I think. Yeah, we are recording. Okay, yes, miss. You got to speak much louder, please. Oh, how do you access the file? Okay, so I have a pin note on Piazza, this guy right here, right there. I think there's also a Quarkus link. So I'm sort of like obligated by the university to put this information both on Piazza and on Quarkus. But generally speaking, I prefer Quarkus. I can update it a lot faster than I prefer Piazza. I can update it a lot better than I can Quarkus. And by the end of the year, the company is going to send me a bunch of stickers and shirts and pins, which I'm going to be able to hand out to any of you who contributed a bit. Right? So if you get like this top contributor thumbs up or check mark, I will give you a physical check mark at the end of the year so you can show off to your friends. Yeah. Go to the bar, be like, check this out. Piazza top contributor. All right, mappings and functions. This is pretty important because, in my opinion, the one thing that most students who come to university have a deep misunderstanding about is functions. And given that a function is probably one of the most important objects of mathematics, this misunderstanding is a crucial one. So we're going to talk a lot about precalculus, and I'm going to show you and develop some of these precalculus notions with a lot more rigor than your high school teachers are probably given. So please stop me if you don't understand something, because I guarantee you other people don't understand. And I may be introducing new symbols that you've never seen before in the past, so it's important that you stop me and tell me if I introduce something new. Okay. You guys know what a mapping is? Mapping's very easy. Right, so let's start at the very, very beginning. Forget about functions and everything else you've learned from school. We're going to start at the very, very beginning. So the other class I taught you about sets, right? So you can have a collection of numbers like 1, 2, and 3. Or you can have a collection of numbers like the naturals or the reals. If you give me two sets, like A and a set B, I can tell you how to associate members of A with members of B. And when I give you a rule associating members of A with members of B, that's called the mapping. And when we have a mapping, it's typical to write F takes A and gives you back B. Right? So this notation is basically a shorthand notation for A maps to B under F. Right? So a mapping is just a rule. And let me show you one of these rules specifically. Here's a mapping. It maps the set A, which are the numbers 0, -1, 1, -2, 2, to the set B, which contain at least 0, 1, and 4. Okay, so the interactive part of these lectures. If I tell you that this is the rule for the mapping, what is f of 1? 1. What is f of 9? Pardon me? Yes, we don't have that information. So I'd say something like does not exist or undefined. Right? Undefined means you didn't tell me what 9 maps to. I can't tell you what 9 maps to under this mapping because you didn't define it. Right? So we learned two things, right? That you can basically make a function of anything to anything. You can relate any objects to any other objects. A could have been a collection of vegetables. Yes? Pardon me? Yes, of course. Yeah. Just not now because I was up till like 1 in the morning creating them. So you're the beta class, right? So you're going to have the most amount of mistakes and the most last-minute stuff. So for you guys. Right. Okay, so a mapping is simply a rule that takes members of one collection to the members of another collection. And you can express this rule in whatever way you want. Once I give you information about how we take members from one set to the members of another set, we can define a few operations. Right? So the important parts about this function, A to B, are two properties, the domain of the function and the range of the function. Right? So the domain, well, I'm calling it a function, but really what it is a mapping. Right? So the domain of a mapping is the subset of A. So I'm saying I'm taking numbers from A, or objects from A, and mapping them to objects from B. So this says that the domain of F are the subset of A for which there is a rule bringing A to B. So I'll say that again. The domain of F, and this colon equal means I'm assigning this to be equal. This is a definition. Right? It's equal because I'm saying it's equal. The domain of F is equal to the set comprised of all A's in A such that F of A is defined. Right? So you learned this in high school in practice by us giving you rational polynomials and you having to figure out where poles were. But much more generally, this is what the domain is defined to be. So what is the domain for this mapping? All A for which there is a mapping from A to B. Pardon me? You're missing a couple. Oh, I like the way you said it first. How about we say -2 to 2? Yeah. Yeah, so the domain of this is -2 to 2. Or more specifically, it's the set -2, -1, 0, 1, and 2. Because sometimes when we say -2 to 2, what does that mean? How many numbers are in between there? Is it over the reals? Is it the integer? Should I be counting by evens? Or sometimes these dots hide a bunch of information. So it's just that easy, right? I give you a rule, and the domain of that rule are all the members for which a rule exists. The range of this mapping is basically every member of B which is reachable. But I can write it like this. The range of this mapping F are all A from the domain, and then you send it through the function. And I'll show you how this works. But intuitively, it just means what are the points that are reachable by F? So I'll work through this one with you. All right, so if you ever get stuck when we ask you, what is this? Right? Step one is to always just write down the definition, right? Because normally there will be a definition. So all I've done here is write down the definition of the range of F. So as I stated, the range of F is equal to the set F of A such that A is in the domain of F. I'm now going to replace this domain of F with the domain of F that we calculated, which is 0, -1, 1, -2, 2. And now I'm going to put those A's into the F's and get this. And then I'm going to resolve each of those functions to get that. And what's the last step here? Is this a set? Yeah, set should be unique. So I actually shouldn't include duplicates in this. So the range of this function is 0, 1, 4. Okay? Domain and range aren't necessarily a product of pictures. Right? This is saying I have a mapping, I have a rule. The domain of the rule is all things that I'm allowed to map. The range of the rule are all the things that get mapped to. Graphs. What's a graph? When you draw a function, what are you drawing? I'm often going to ask you these things about what is this object that you've taken for granted for like 10 years? Just to prove to you that it is sort of more sophisticated than you may think. Yeah. That's close. Yeah, that's pretty good actually. But it's a certain x and y. Right? So if I give you an equation, you only want to put dots for the x and y that are so-called satisfying that equation. Because the whole, if I draw like the xy axis, that's just technically the entire real plane. That's an infinite amount of points. So you want to, drawing a line through that plane is saying, I just want these points and not all of them. But we'll flesh that out a bit more. So if I give you a mapping that takes real numbers to real numbers, that is, I just give you a rule, right? Maybe I take x to x squared. I can generate a collection of points that satisfy that function, right? So if I give you a mapping, I can say that I want to collect all the points x, y, such that x is in the domain of f and x maps to y, right? So fundamentally, what that would mean for this mapping is that I just have to plot out 5 points. 0, 0, minus 1, 1, 1, 1, minus 2, 4, 2, 4. Right? I could draw the information rather than providing it to you in a table. So, this funny looking G is the symbol for graph, right? And the graph of a mapping is the collection of points that satisfy the mapping. And we can draw those or list them in a table or list them as a set. But the point is these are all equivalent representations. Don't worry, I always have an example after I give you these sort of definitions. So I gave you a mapping F, right, that table, and the graph of that mapping are just these collection of points. 0, 0, 1, 1, minus 1, 1, 2, 4, minus 2, 4. So this is an encoding of the points in that mapping. Just a single, so mathematics, all it is an encoding. Right? The first question I said is I gave you a mathematical description and I converted it to English. So it'll always be like a symbolic representation, an English description, a geometric representation. All things are equivalent. And we have to learn how to move in between these spaces to find where the question is most easily answerable. So let me give you another encoding of the graph. There you go. Right? What are these? What am I showing you? Well, this is the point 2, 2, 2, 4, minus 2, 4, minus 1, 1, 1, 1, 0, 0. So I just show you 3 ways to define these relationships, right? Relationships among 5 points. I gave you a table, I listed them out in a set, and I gave you a picture. Right? All of these things are the same. It's just a way of communicating these are the points that I care about somehow. So whenever you give me a graph, or whenever I plot something, this plot, really, you should be interpreting this as a way of visualizing a collection of points in space. So this was a mapping on 5 numbers. This is now a mapping on an infinite collection of numbers. I'm going to say, let's now take a mapping which goes from the reals into the reals. And the rule I'm going to give you for this mapping is that you give me x and you get back x squared. Okay? So give me 1 point in the graph of this function, or of this mapping. 1, 1. Give me another one. 2, 4. There's the rest of them. So when you see this, there's many things that you have to see here. You have to see, oh, this is a parabola and all the consequences from that. But you also look up there and see, oh, these are an infinite collection of points, all of which satisfy a certain mapping or property. Right? So all of the points on this plot satisfy, they're all x squared. Right? So I could tell you. So what's the difference between this plot and like this rule? Nothing really. Right? Except that you can only pull values off of this plot for as much as they show you. Whereas this gives you the rule for everything. Any questions so far? Right? So understand that when you're drawing shapes in space, these shapes are telling you about equations. Right? These are points that solve equations. Whoops, I just gave you the answer. Well, the collection of points for this plot, or this graph, I can generate like this, right? The points on this curve are the points x squared, such that x is in R. But these are all equivalent definitions of the parabola. Okay, so now I'm going to test your capacity to understand algebra and to convert it to a geometric understanding. I'm going to give you 2 statements here. These statements are the same. They're mathematically equivalent. And I'm going to give you 2 graphs. I want you to think which graph satisfies this. So this is a condition. And something can either satisfy a condition or violate a condition. So the condition I'm giving you here is this one. If I give you a mapping F, and that mapping F takes A to B naught, and it takes A to B1, and if that's the case, that it is the case that B naught is B1. Or equivalently, if A, B naught is on your graph, then A, B1 is on your graph, then B naught has to be B1. Right? These are 2 equivalent ways of describing a property. Which one of these plots satisfies that property? Yes, miss? You're too good. She's right. Do you recognize this at all? What is this property? Oh, here's the spoiler. You know this. You've seen this a million times. You just know it of a different name. Which one of these is a function? Yeah, you again, miss. Left. Why? Because it satisfies the vertical. Which one of these two satisfy the vertical line test? What is the vertical line test? Yes, sir. Just point at the slide. Yes, correct. That's the vertical line test. This is the vertical line test. How did you not look? You need to realize this now. Vertical line test means that if I strike a line through a function, that it can't hit the function twice. That means there can't be two spots on the domain for which you get the same y value. That means if you find 2 points that go to the same y, they have to be different. I have to flesh this out a bit more, but this is the vertical. So let's ask what this says. So if this is the vertical line test, F1 should violate this condition, yes? Okay, so here's a point, let's call it 2, and it goes to here, and it goes to here. Or that means I found 1 point, 2, such that 2 goes to something negative, and 2 goes to something positive, and something negative is not equal to something positive. So it doesn't satisfy this condition, which means it violates the vertical line test, which means it's not a function. And more proof that, so if I were to ask you on a, well, here's my next question. Okay, so here's the vertical line test. A mapping, if I give you a real mapping that takes reals to reals and maps x's to y's, this satisfies the vertical line test when this condition holds, right? If you have f of x and that goes to y naught, and you find another x and that goes to y1, this y naught and y1 have to be the same, right? You can't get to the same altitude twice, right? So, would you be able to write me an algebraic statement for the horizontal line test? Or sorry, wait, vertical, yeah, horizontal is this way. So could you write me an algebraic statement for the horizontal line test? What are we trying to eliminate in the horizontal line test? Yeah, this is where I'd like to go to the board, but then everything's lost in video. Well, sorry, YouTube. Okay. So again, this doesn't satisfy the vertical line test. This is f of x. I'll have some point here called x. This may be y naught, and this may be y1. And we have f of x is y naught, and f of x is y1, and y naught is not equal to y1. Horizontal line test, right? This parabola would fail the horizontal line test. Why? Well, because there's 2 things that go through. If I write a horizontal line, there are 2 things that go through it. That means I should not be able to find 2 points, A and B, such that f of A is equal to f of B. Right? So if I find 2 points A and B, such that f of A is equal to f of B, it must be the case here that A is equal to... Did I just write down the same thing? Did I do it again? If f of A is equal to f of B, and this is the case, then this has to be true. Oh yeah, so it violates the horizontal line test. Anyway, so give that a ponder. Oh yes, that's correct. Any questions so far? Because this is mostly pre-calculus with a different twist. Like, I'm not trying to teach you this material. I'm just trying to show you a different angle on it. Yes, sir. For this one? Sure, I put y for here. Yeah, I'm saying, look, you really do get 2 distinct values here, right? Because you don't know what they are ahead of time. right? If I gave you the set version of this, a collection of points, it'd be up to you to go into that set and find two pairs that violate the property of the vertical line test. Okay? But you need to sort of begin to understand how these geometric, like we told you about the vertical line test because that's easier to conceptualize than the algebraic rule. But now that you have to actually do work, the algebra now becomes a thing that you need to use, right? Like the vertical line test is good intuition, but it's not a sufficient tool when you actually want to demonstrate something, right? Because you can't do math by showing a bunch of pictures, right? The pictures are supportive. The algebra is really the thing that's actually like helping you prove something. Where are we? Okay. So we're talking about mappings, and I've been saying functions, right? And that's wrong. Every mapping is not a function, but every function is a mapping, right? So for this course, we're not really interested in mappings. We're interested in real valued functions, right? That is a very specific mapping which maps real numbers to real numbers, and the mapping has to additionally satisfy the vertical line test, right? So what this means is that when you have a function and you give it a number, you get exactly one number back, right? If I asked for what the value at x was here, this is basically the square root function on both sides, right? The square root of 4 is both 2 and negative 2. That's why it's not a function, right? You really have to expect something unambiguous back, a single number. So if you have a mapping which maps real numbers to real numbers, and that mapping also satisfies the vertical line test, this mapping is called a real valued function. And when we have real valued functions, we have some nomenclature here. So we usually write y is equal to f of x. Equivalently, that means that xy is in the graph of f. The x is called the independent variable because that's the thing we move, and y is called the dependent variable because the value of y depends on the value of x that is given. And it's not always the case that x is independent and y is dependent. This is the other thing you sort of have to get over. I'm going to switch things all the time. We may set y to be the independent variable and x to be the dependent variable. I might swap out things with s and t. F doesn't necessarily mean it's a function. I may use g, right? So the symbols and letters I use are going to have a contextual type of meaning, right? So it sometimes gets confusing when I switch an x to a t, but it shouldn't, because you need to see these things as being descriptions of rules, right? And I can describe a rule in many different ways. Okay, so now we're sort of approaching the type of math that you're getting more comfortable with, right? So typically, like really a function and a graph, we represent like this. So now we see this as being a description of an infinite amount of points that satisfy the function f, right? So if this was 1, this is the point 1, f of 1 up here. And actually, it will become important later, but since this f1 is the y distance, or since this f1 is y, the distance from the x-axis to that point is given by f of 1. Well, in this case, because it's positive. But arbitrary points on this function are just x, f of x. And that's precisely what it means to be on the graph. And this distance here is f of x. Any questions? And so this just should all be, I don't think we're going to be doing any sort of 3D plotting. Maybe when we do spinning. But otherwise, we're going to remain in the plane. Yes, miss? Why is any of this important? Well, I don't know the scenario, but you may have like a real world scenario where you'll want to like eliminate that. I'm a pure mathematician, so I just say things like, I do math because I think it's kind of neat, right? So sometimes I'm just going to give you something because I think it's personally interesting. So I don't know. Let me try to come back to that. I don't know when the horizontal line test would be. Well, for instance, I could say if we wanted to reflect everything. If I asked you a question like, if I took this function and reflected it among the y equals x axis, would that be a function? The precondition for that would be it has to pass the horizontal line test. But that's really contrived. But good question. Maybe I'll put that on your quiz or something. get you to like use the horizontal line test somehow. If you needed to like map something to something unique, if I needed to associate every one of you with a student number, and I plotted that, that would have to pass the horizontal line test. Otherwise, I gave two of you the same student number. I did it! See, math is useful. Okay, so here's a function. Let's recall. Let's prove to me how much you remember from high school. Here are two mappings. X plus y equals 4, and x squared plus y squared equals 4, which correspond to functions. Now, don't rush. I want you to think about what I've asked and ask me clarifying questions because you need them. Yes, sir. Okay, what's the answer? Why? Neat. That's correct. But what I also wanted you to yell at me for was you didn't tell me what the dependent variable was. Because I bet you all assumed that it was x, right? So just because we usually have x as the independent variable, you shouldn't rush in assuming that, right? So you probably should. It doesn't matter. Yeah, I know. In this case, it doesn't matter which one's which. You get the same line in the same circle in both cases. Was everyone able to identify number 1 as being a line? Good. Was everyone able to identify number 2 as being a circle? What's its radius? 2. Okay, great. Oh, use Desmos. Okay, so I'm going to show you how to use a tool, which is super useful. Okay, so first of all, you can just plot from here, like right from the Google search bar. You can say plot y is equal to x plus 4. What? There we go. Oh, that's 3D. Damn you, Google. Maybe I have to do this. All right, there you go. Okay, so you can get rapid plots just by typing into the search bar here. You can also do things like plot, what is going on? Plot sin x. And it like gives it to you. But there's a better version of this called, is it Desmos? Yeah, Desmos. Can everyone see this? D-E-S-M-O-S. Does anyone know about, am I showing you something that you all know how to use already? Well, tough luck. Okay, so most of you know how to use this, which is a good sign. So I'm just going to plot those two functions. It doesn't like it. Oh, I think maybe I need an expression. Okay, great. So there's the line, and it obviously passes the vertical line test. Does it pass the horizontal line test? Yes. So another way, so in order for a function to be called one-to-one, it has to pass both the vertical and horizontal line test. So applications are just flooding into my mind now. Let's plot the other one. Y squared plus x squared is equal to 4. Oh, it's a small circle. Let's make it bigger. 40. Okay, so this is a really useful tool, and you should use it because you can like zoom in and you can like, I don't know, hit this thing and it does stuff. I'm super good at teaching. Okay, so we'll return to this later, but it's a very, very useful tool for rapidly graphing. Just try not to get over-reliant on it because you don't have access to this on your midterms and tutorials. But you should use it if you get stuck. Okay, you told me that this doesn't satisfy the vertical line test. It's the circle. Okay, prove it. Prove it. Okay, so I have to use algebra, right? Okay, so if I were to ask you this in a tutorial, and I'd say demonstrate that this fails the vertical line test, I think some of you would get kerflustered. Because you just say it's a circle. Look, it's a circle. I could draw a line and it hits it twice. And you'd be right to a first approximation. That is the sentiment that you would be required to encode mathematically. Yes? Not enough proof. But you need to write the algebraic version of that drawing, is what I'm trying to say, right? Because you chose a very particular line, right? That's not, so what is the best way to show something doesn't satisfy the vertical line test? You show that it has to fail the definition for being a function, essentially, right? So what does it mean to fail the vertical line test? That means there's some x in the domain which maps to two different values in the range. So all I have to do is say, look, here are 2 points on this graph with the same x with different y's. This fails the statement of the vertical line test. So there it is here specifically. So if I rearrange things a bit, you end up getting the function f of x is equal to plus minus 4 minus x squared. When I write it like this, it becomes obvious that it's not a function because plus minus will always give you two things. But this is the best way to prove it, right here, right? So you could have written a whole page of sort of hand-wavy explanation pointing to your circle, but all I would have been looking for is these three statements. Look, 1 square root of 3 is in the graph. 1 minus square root of 3 is in the graph. And root 3 is not equal to minus square root of 3. Right? So we fail the vertical line test. Right? The requirement was that we would never be able to find such points to satisfy the vertical line test. Okay? So geometry is good sometimes to get to figure out what you need to write down algebraically, but often it's insufficient for actually giving a rigorous argument. Right? Argument has to come through algebra. Any questions? I'm getting scared by the lack of questions being asked. Yeah. We'll put the square root of 3. Okay, this is how I got it. I basically took the circle. I knew this is radius 2, so I picked 1 here. And then if I pick 1, you end up getting the square root of 3. So just look at the function, right? So it doesn't have to be that one. I could have chosen any 2 points. I could have made x. Well, what's the only thing I can't make? Oh no, even 0 would work in this case. Maybe I should have picked 0. 0 would have been better, because 0, 2, and 0 minus 2 is in the circle. Right? But anyways, you just need to show it violates it once, because the statement is about all the points you satisfy this. So if you find 2 points that violate it, you're done. So, but there's an infinite number of ways that you can show that this violates it. Yeah.
Say the vertical line test algebraically before our answer?
No, you don't need to tell us stuff that is defined in your book. So if I say things like use the product rule, don't write the product rule. Again, not biology. Yeah. Sorry, I'm going to dump on biology a lot, but I actually have a deep respect for that discipline. It keeps me alive. Yeah. You're asking for steps. I want you to understand what we've done. Okay? I gave you a property, vertical line test property. I said, show me that this fails this property. So there's going to be a myriad of ways that you can do that. One of the ways is to do this sort of back substitution, but fundamentally all you're trying to do is find 2 points in the graph that violates the condition. What if I gave you a graph? What if I didn't give you the function, but I gave you a picture? Then your method of trying to work it out would fail utterly, right? So this is the mode I'm trying to get you out of, right? There is not one way to solve every problem. I swear to God, if I could say, for this problem, solve it like this, for this problem, solve it like this, I would. It would make instruction 100 times easier. But that's why this is difficult, right? Because so I think of math as I'm giving you tools. Like, here's a hammer, here's a wrench, here's a screwdriver. And I'll often say this expression, here's another tool for your toolbox. So when you come and try to solve problems in math, you open up your toolbox, you try the hammer, you try the screwdriver, but you may not you may not find the right tool until the 10th tool down. And the only reason I know which tool to use better is because of experience and intuition, which is impossible I can't teach you experience. You have to develop experience. But this is why I'm trying to get you guys to do so much work, because I genuinely believe I can get you up to a capacity to never have to, so you can get the outcome you want and never have to look back and go life science your way to victory. I don't know. I just have to mention, though, that if you guys legitimately are life scientists, you're going to have to do probability and statistics. And that entire discipline is applied calculus, essentially. Right? So this term, we're going to show you a little bit about probability, just to prove to you that we're not teaching you calculus for no point. It's actually extremely important for statistics and probability. Yes, miss?
I was gonna ask a question, but then I realized you were gonna take it up now.
Which one?
Like about the horizontal line test, but
Oh, yeah, I guess, eh? This is what happens when I write slides at like 2 in the morning. I forget what I wrote. Write an algebraic rule for the horizontal line test and show that, what is this shape? Parabola. Where does it hit the curve? Or where does it hit the x-axis? One in what? 1 and 2. Does it point up or down? How do you know that? What's positive? Yeah. You just have to look at the leading term on the x squared, and that tells you the positioning. Okay, so the parabola shouldn't satisfy the vertical line test, right? Horizontal line test. I always forget. For any of you who can't remember the difference between vertical and horizontal, like me, horizontal, horizon. You're welcome. Okay, so the horizontal line test means that we shouldn't be able to find 2 points in the domain which go to the same place in the range. So all I have to do is demonstrate that I can find 2 points in the domain here that map to the same place in the range. And that's quite easy. I pick f of 1, and that brings me to 0. And I pick f of 2, and that brings me to 0. Right, so I violated the horizontal line test. Okay? So you need to gain some experience converting these geometric rules back to algebra and converse. Yes, sir. Well, what kind of question would I ask you here? Ask me the question you want to ask. No, you're asking something about maximizing the amount of marks you're going to get on a test. So if you're going to ask me that question, be honest with that question, and I'll tell you how to get the maximum amount of marks on the test. Oh, okay. Sorry then, yeah.
I'm just asking if we have to define the vertical and horizontal line test before answering the question, or we can just write down the answer.
That surely sounds like a question about maximizing marks. We're not going to have you repeat definitions, okay? Because I don't want you to have to memorize anything. If you try to memorize stuff, the tests are going to be designed so you'll fail them, right? You won't have to, I'm never going to say, write the definition of this down on the paper, right? Because I'm assuming that you know them. Because if you don't know them, you won't be able to answer anything, right? If you don't know the definition of tangent, and I say, find the tangent, you're done, right? So you will never get marks for dumping your knowledge onto the paper. You will get marks for genuine progress towards a solution, and we're going to teach you how to maximize those marks. But again, it's thinking that I have to get you guys good at. It's thinking and writing which is going to get you the top grade in this course, even when you don't answer the question. Right? So that's what I'm trying to get you guys to do. Earn marks even when you can't solve the question by figuring out how. But horizontal line test is just something I invented so that we could talk about these relationships, right? So I don't even think I'll ever ask you a question about the horizontal line test. Yeah. Well, what does a horizontal line test have to do with being a function?
But can't you still satisfy the horizontal line test and still be a function?
Yes.
So we would never use the horizontal line test to prove, oh, this is a function or it's not.
No. I just introduced it as a learning tool. So I may do this often, right? Just show you something interesting. I know you're all hyper-focused and taking all this knowledge and inserting it into your brain so you can take it out and put it back on the test. This is different. This is different than when you took calculus the last time, right? And we're doing it different on purpose, right? Because we need a different sort of attack angle on this course to get different results than people have gotten maybe 1 or 2 times last. I'm really trying to get you to really understand the algebra geometric relationships, and the rest will become easy. I swear to you, as soon as you get this relationship in your mind, you'll start understanding things. You'll start making these disparate connections, okay? So I'll help you. I'll help you all get the best marks on these tests. But that will come by thinking and practice, right? Not by memorization and reproduction. I'm sorry. If I could do it that way, I would. But, okay. So the horizontal line test is just a fun, neat thing that I introduced for no reason, right? You'll probably never see it again. Okay, but this is how the lesson here is to show how to demonstrate something violates a property, right? Which is an important thing to understand. There's this notion of natural domain and range, right? Because normally when I write down a function, I don't say this is the function's domain and range. Sometimes it's up to you, the student, to extract it, right? So this should be from pre-calc. What is the domain and range of this function? Okay, so what is the domain as I defined it earlier? I can write it. So how do you find the collection of x's for which f of x is defined? What's an equivalent way to find this set? Okay. What's the opposite of this set? Everything that's not in it. So yeah, to find this set, you can simply find the collection of points where this is not defined and take the opposite. Yes, miss? Yes, x can't be -1 or 1, right? Because you can't divide 1 divided by 0 equals undefined, right? So that's why it is not in here, right? Because f of 0 is not defined, so it wouldn't be in this set. So there are two ways to write the solution to this. Oh, sorry, here's a picture of the parabola. Well, this isn't a picture for that plot, though. It is a very handsome looking parabola, so just ignore that. Or in your mind, divide through by 1. Okay, Desmos to the rescue. What was it? X minus 1, x plus 1. All right. So that's how it looks. Okay. So the natural domain, you can write it like this. This is a neat way of writing it. Right? This says R, just remove 1 and -1. Because otherwise you'd have to write 3 intervals. Right? You'd have to go to -1, then from -1 to 1, and then from 1 to infinity. And so sometimes you can just say it's not this, right? Or you can say the converse or the complement of -1, 1 in the reals. So what's the range of this function? I'll just hide this. And again, this isn't the plot, right? Yeah. Oh, okay. Yes, anyone? Well, let's think about this. So the range should be all the things that are reachable, right? So I have a fraction. So I should be able to get everything that's fractional, right, between -1 and 1, surely. And then if I start dividing 1 by something that's tiny, I start getting big numbers. So I think that I should be able to go all the way to -infinity if I put something tiny, if I put something huge in the denominator. And I should be able to get to +infinity if I put something tiny in the denominator. Right? So if I put sort of something like the square root of 0.999, right, would be dividing by 0.1, which would be 100. Right? So the plot, this is when the geometry is a better look here. It's very obvious here that you're going to get everything from 0 to infinity, but we're actually missing what? 0 to -1? Right, so the range actually is going to be negative infinity to negative 1 inclusive, and then 0 exclusive. We never quite get there. We have poles to infinity exclusive because you never reach it. Okay, but you're going to go home and figure out how. So by looking at the plot, the range was super easy to pull. Now figure out algebraically how to get that same result. Right? How can you algebra it out that you're missing 0 to negative 1 in the range? I guess it's easy with the plot, but now work it out with the algebra. Right? That's the number one skill that I'm trying to imbue in you, students. Is it okay if I keep would you rather be let go early or would you rather be given breaks? You'd rather go early. That's what everyone always says. Okay. So what is the natural domain and range of y equals 3 plus square root of x? What are the permissible x values for this question? Can x be minus 1? Yes, sir. All real numbers 0 and above. Sure. That is correct. What is the range? What are all of the attainable y values? Perfect. So we'd write it like this, right? The domain of f is 0 inclusive to infinity, and the range is 3 inclusive to infinity. Hello. Welcome. Have a seat. Yes, sir. Can I? See? As predicted. You start at 3 and you start increasing. And you get everything from 0 to minus and to plus infinity. Just wanted to visit, I suppose. I haven't yet defined even, odd, or neither. So I think this slide's a little bit out of place, but I didn't give you an answer anyways. I want you to do it at home. So find the domain range, determine if this is even, odd. Just play around with this function and see what you can discover. Does it pass the horizontal line test? What does that mean? So give that a try and plot it with Desmos, just for fun. But even though all of you more or less know how to do it already. Okay, so let's talk about what it means to be increasing and what it means to be decreasing. Now, and there's a little bit of a nuance here which is important, especially given some of the questions that I assigned in your Weeby work. Okay, so whenever I write this now, this means I want a real valued function. So this is a mapping which is also passes the vertical line test, which takes reals to reals. So let f be a real valued function. Let I be a subset of the domain of f. Right? So I'm going to take some of the points where f is defined. F is increasing on I. Oh, this is a little bit... I really needs to be an interval here. I should change that. So you really need to go from like A to B. You can't have like skip. So I'll change that. So f is increasing on this interval. Right? And here is the algebraic description of what it means to be increasing, which I hope then we can like associate with an increasing function. So if you think, what does it mean to be increasing? So if I have a function, like a drawing of a function, and I pick one point on that function, and I go a little bit further down x. So if I have x, and it's here, sorry, I'll go above my laptop. So I have x, and it goes up to here. If I go a little bit further down the real line to another x that's further down, that should be higher. So the property should sound like this. If you give me two numbers, and the first number, x0, is less than the second number, x1, then the function is only increasing if the value, f of x0, is less than f of x1. Right? You have to be increasing in your y's. Right? So if you have 1 and 2 on the domain, the function needs to be increasing only if f of 1 is greater than f of 2. So I can see there is some discomfort with expressions like this. So how can I help you? Right? How can I help unpack this? Yes, miss. Oh, I think this should be flipped. You found one of my famous mistakes. I'll change it. Should actually write these down. But that's good. That means you, it's good if you catch my mistakes, because that means you're actually like, you understand enough to know that I screwed up. Just take it in a bit. Take it in. It's like, what can I help unpack? Yes, miss. This thing? So I'm saying take 2 points and assume one of them is smaller than the other. So like basically, if I were to do the geometric version of this, here's the real line, there's the real line, these are the x's. So I'm saying you have an x naught here, and it goes through here. So this may be x naught f of x naught. Okay? And if I go down here, x1, if this is further down, then this point, x1, has to be higher, yes? Which means that this number has to be smaller than this number. So that's exactly the property I wrote. If you find x naught and x1 so that x naught is smaller, then it has to be the case that f of x naught is smaller than f of x1. Yes, miss? Yes, indeed. Yeah. Yeah. Yes. Either I think I was supposed to either flip this or flip the inside, but it's good that you realize this. Yes, sir.
Could it be kind of explained that if the y's increase, or sorry, as the x's increase, the y's increase, and therefore it doesn't increase on function? Or
As the x's increase, the y's increase.
could you say it that way too?
That's an English statement, though. So how you would need to convert that to this before it would be useful. But that's a good intuition about the so like you always need these three, you need the 3 points on this triangle. The algebra description, the English description that you just gave, and the geometric description that I just drew on the board. Right? All 3 pieces. And you've got to be able to jump in between them. Because I assure you that we're going to give you questions where, depending which end of the triangle you're on, it's either hard or super easy.
But what I just said is correct.
Technically, but that's a good first approach. Yeah, it's not incorrect. I can definitely say that. Yeah. So notice, though, that, okay, so let me ask you a question. If I gave you the constant function, actually, did I do that? Oh, according to this definition, is the function f of x equal 5, just the line at 5, is that increasing or decreasing? Who said that? Very good. It's neither. Why? Yes, miss? That's correct, but how would you demonstrate that it fails? Yes, sir. Oh. Pardon me? Well, those are variables. You got to give me something more concrete than that. Yeah. Well, but sure, but what does that tell us? I gave you a property. I said a function is increasing if it satisfies this property. So it's not increasing if it fails the property. Where are we getting this idea from the slope? How do you know that? What does the slope have to do with increasing or decreasing, aside from the fact that your teachers told you that when the derivative is positive that you're increasing? Yeah, so we're going in a circle, right? Like the fact that the slope is giving you increasing information is because of this, not the other way around. Okay, it's true, but I'll say something more severe. I haven't introduced slope yet. So we shouldn't use tools that are like haven't been introduced yet. Okay, that's what I'm looking for. Like two honest to God numbers, right? F of 0 is 5. F of 1 is 5. 1 is bigger than 0. 5 is not bigger than 5. We've now violated the condition of increasing. Right? It's because it's strict and not strictly and equal. Right? So there's something called non-decreasing. So the constant function is non-decreasing. It never decreases. but it never increases. Funny enough, this is also non-increasing. A constant function is kind of special. So you actually have 4 categories: increasing strictly, decreasing strictly, non-increasing, non-decreasing, and constant. Right? But there is a little nuance here, right? So the other lesson I want you to learn here is when you have to violate a rule, do it as specifically as possible. You don't say it works for all the x's. That's technically true, but you only need 2 points to violate the condition. If I ask you to prove something isn't the case, you just have to give me one example how it fails, and that's enough. The following parabola is an even function because of symmetry about the y equals 0 axis. What's the algebraic condition for being even? Okay, so let's investigate this a little bit. So if I pick a point on this parabola, there should be a symmetry about the y equals 0 axis. So that means if there's xy on the one side, I should find what on the other side? Sure, minus x, y. So what is the algebraic condition for even function? Yes, miss? Yes, you're saying this one, correct? Okay, so I'm going to do it in 2 pieces, right? So these 2 statements are equivalent, just so I can reinforce some of the old notation from the beginning of class. If x of y is in your graph, then minus xy has to be in your graph. Right? That's another way of expressing the even function condition. Right? This is the way that you're typically been shown it. Right? So I don't want you to get confused though, because if I say, what is a function that satisfies this? You're like, oh, I don't know. Right? There are many ways to write equivalently a condition for something. So it's helpful to see multiple ways of approaching something. Yes, miss?
Notation number 1 have a specific thing?
This G?
No, the whole type of notation versus 1 and 2.
Oh, what is this? I guess this would be called first order logic then, since there's really 0 English in it. This is how I prefer writing, right? Because the less English you write, the less ambiguity that you're introducing, and it forces you to write down exact statements. Right? So generally speaking, less is more in math. You don't have to write down much. You just have to know what the right symbols to use are in the right conditions. Okay. So here's the definition. Let f of r to r be a real valued function. Then f is an even function when f of x is equal to f of minus x. Here's a cubic. It is an odd function because of symmetry about the y-axis. Y equals x-axis. That means you have to flip in the vertical axis, then flip in the horizontal axis. What's the algebraic condition for being odd? Yes, miss? Could you give it to me in the graph form? If x of y is in the graph of the function, in order for that function to be odd, what other point has to be in the graph? Sorry? Yes. So I'm sorry I pushed you a bit because I feel that this is just recalling from high school. Right? But those 2 statements are exactly the same statement. Right? So I don't want you to recall from memory. I want you to try to access the visual parts of your brain. I'm always just reconstructing these rules by remembering what they have to do, which gets you a lot more. You can do a lot more of that. Okay, so the following are equivalent and correct. So a plot is odd. If xy is in the graph, then minus x minus y has to be in the graph. I can write that a different way. That means if f of x is equal to minus f of minus x, then this is an odd function. 1 or 2 is better for, if I asked you to confirm a function was odd, would you use 1 or 2? 2. I would use 2. So here's the definition of an odd function. Let f of r to r be a real function. Then f is odd when the following is satisfied. F of x is equal to minus f of minus x for every x in the domain. Let's test your knowledge. Is there an everywhere decreasing even function? I want you to take a few minutes to think about this one. Because these are all terminology that you should be familiar with from pre-calculus. Yes? Good catch. Oh, talk, chat. 2 minutes, 3 minutes. I want you to think about it. Right? Oh, are you trying to indicate to me the answer? Can you prove it?
Oh no, I was just trying to grab from the last slide.
Oh, okay. says no? Who says yes? Who's abstaining? Okay, so we have a yes. So you have to give me an example then. Oh, but so it's then okay, so you're correct with one minor incorrect aspect of that. You restricted the domain. I said everywhere. Right, so you cheated kind of by saying, oh, yeah, I'm going to redefine everywhere to be half of everywhere. So, correct, but you cheated. Okay, so does anyone have an answer without cheating? The answer is no. Can anyone give me an explanation as to why it's no? Yes, sir.
So if you take like an example of 2 points, say -1 and 1, and it's a decreasing function, therefore the y's cannot be the same.
Wait, you gave me 2 points.
Sure.
That's not a function.
No, I'm saying like let's say function
That goes through those 2
yeah,
points.
like
Okay.
y equals -x, and it goes through points -1 f of 1 and 1 and f of 1, and therefore those f of -1 and f of 1, which are the y's, they cannot be the same because it's decreasing.
Yes. Okay. No. Right? If you have an even function, this means that if you find, you take any point from the domain, you're going to find the same y on the other side of the real axis. Right? There's reflections at every bit of these points. Well, that means you found 2 points which are at the same y. That's not increasing, or that's not decreasing. Well, it's not either. Right? So no, every function that's even, every even function f has an a where f of a is equal to f of minus a, with a positive and minus a negative, right? That is to say that they're different. This violates the condition of being decreasing, right? So when we ask you to prove something is or is not is easy. You just have to show that it violates the condition in one instance. You don't have to write a long story describing something, right? This is the power of utilizing the algebra of the problem. But you may need to look at the geometry in order to get the algebraic statement, right? So geometry, English, math. Is there an everywhere decreasing odd function?
Just a quick question about that. So if you would have just changed the wording and said, is there a decreasing even function and just omitted the everywhere, the answer is yes if you restrict the domain.
Because yes, yeah, you would have technically given me an everywhere decrease. You would have technically given me a decreasing even function. Although I'm not sure that even has. If you restrict the domain, that's still an even function. I don't know about this one. I don't know. The spirit of my question was for the full real plane. What is there an everywhere decreasing odd function? Yes, miss. Perfect. Wait. That's increasing. X cubed. Negative x cubed. I made the exact same mistake last night. Yes, minus x cubed is odd and everywhere decreasing. I'm going to come up with the best horizontal line test question now for your midterm just to troll you guys. I'm here. Aww. Okay, so but be ready on your tutorial. We're going to ask you one of these questions, which is like demonstrate something, which means you're going to have to use math, which you'll probably fail at doing, which is our expectation, right? So you should be trying to maximize your partial marks by trying to work through the problem-solving framework.
Sorry, when you say demonstrate, are you referring to the even and odd questions that you've been putting up so far? Is that
Well, I usually say, here's the property. Show me that this either satisfies or breaks the property. Right? That's a little bit different than these questions where we're like, calculate the slope, and you give me back 7. This is more of like an argument that you have to give us. Right? We're just trying to warm up your gray matter. Right? Don't be too stressed about these quizzes. Normally, these quizzes, like the first half is quite easy. Right? So you for sure will get half of it, and like the second part's a little bit more difficult, but they're only worth 2%. Right? So
That's still marks, 2% still. I
Yeah, but you got to stress about the right stuff,
Yeah.
right? Like stress about the midterms, stress about the finals, right? Don't stress all the time, right? Because then that's also going to kill you, right? So I would give you no marks for these. So here's the problem. You make something worth nothing, no one does it. You make it worth too much, everyone cheats. So you have to find like this balance, or 1 or 2%. You should be able to get at least half of them. Okay? I'm much more concerned about you getting things wrong in the midterm and final, where that's like 8% of your mark, 7% of your mark when you get things wrong. Right? So stress about that. That's appropriate. Okay, so we should quickly go through the rest of this stuff. Like numbers, functions could be added, subtracted, multiplied, and divided. So given two real functions, f and g, then we have that f of x plus g of x is equal to f plus g of x, and f of x times g of x is f times g of x. So what is this saying here? What is the point of this? This seems like the same thing written twice. Like, what is this rule saying? Did I actually tell you anything useful? So what does it mean when I say f of x? That means you're giving x to the rule f, and f is giving you a number back. When I say g of x, I'm saying I'm giving x to the function g, and g is going to give you a number back. And then you can add those. I'm saying that this is equivalent to taking the rules themselves and combining the rule, and then evaluating x in the new rule. So I'll show you an example of this. So for example, if I have x squared and 3x plus 1, I'm going to evaluate the sum of those two functions at 2. So you have f of 2 plus g of 2 is 2 squared plus 3 times 2 plus 1, and that's 11. Now I'm going to do the other way. I'm going to evaluate the rules first and then evaluate. So f plus g at 2 is, oh, I missed the 2 there. So this should be x squared plus 3x plus 1 evaluated at 2. So I'll write that down as a mistake. Which itself is equal to 2 squared plus 6 plus 1, which is 11. Right, so those rules are just basically telling you you can permute the order of like evaluation of x. Right, you can either do x first and then multiply or add, or multiply and add first and then evaluate at x. There's geometric interpretation to these sums and multiplications and divisions of these curves as well. So here are the 3 curves that I gave you. Y equals 3x plus 1, y equals x squared, and there's the sum. And you expect that this point plus this point gives you this point, right? 4 plus 7 is 11. So this point here is just the sum of the 2 points underneath it. Right? This point here is just the sum of the 2 points underneath it. Right? So the arithmetic on the geometry is exactly what you would expect, although the addition's a little bit uninteresting. What's more interesting is dividing two functions, which technically falls into the category of multiplication. So if I give you x squared and x plus 1, let's plot f divided by g and compare the ranges for f, g, and f over g. So what do you expect to appear here? This is going to be a nice plot, like a circle or a triangle, or what's going to happen? Do we get any? Okay, alarm bells need to go off when you see certain things. One of these things that alarm bells need to go off is divisions by 0. Is there a division by 0 here? Could be. When? Okay, so at x equals -1, we expect this function to explode somehow, right? Because we're dividing by 0, which introduces sort of asymptotic behavior. So just keeping that in mind, that's what the plots look like. And let's just walk through it to see what's happening here, right? So the new graph is red, and the old 2 graphs that I'm dividing are magenta and cyan, or purple or pink and blue. Okay, so here's pink, and you divide by something and you become smaller. Here's pink, you divide by something big and you become smaller. It's interesting here, if you take pink and you divide by something close to 0, you get something that's enormous on one hand, and you get something that's negative enormous on the other hand. Right, so there's always this interplay between the graphs and the algebra that I'm going to be repeating endlessly as the term goes on. Function composition, that's when you take 2 functions and you want to combine them. So you can have one function f that goes from b to c. You can have another function g that goes from a to b, and I can stick these two functions together to get a rule that takes me from a to b to c through this mapping, right? We go from a to b by g, and then we go from b to c by f. And so we write it like this. F, and that circle there is composed with g, is equal to the function given in this expression, f of g of x. Is it the case that f composite g is equal to g composite f? Prove it. How would you prove it? Yes? Can I do x minus 3? Because that's the one I did. It's very close to what you recommended. Okay, so yes, perfect. So when I'm asking you to prove something's not the case, you just have to give me a counterexample. So look, just take x squared and x minus 3. If I compose f with g, that's going to be f of g of x, which is going to be f at x minus 3, which is going to be x minus 3 squared, which is x squared minus 6x plus 9. If I do it the other way, you get g of f of x, which is g at x squared, which is x squared minus 3, which is not x squared minus 6x plus 9. Right? So they're not. This is not commutative. You cannot, change the order of these things. So most of the operations that you've ever dealt with are commutative. Can you tell me? Oh, that's not actually true. What operations do you have that you've learned in school that are commutative and which ones aren't? Which ones can't you swap? So a plus b is the same thing as b plus a, but that's not true for subtraction. It's true for multiplication, but it's not true for division. Right? So there's some operations which we can change the order, and other ones that we can't. So you have to be careful. Here's an exercise for you to do. So this is how. So questions will have answers in class. Exercises are stuff that I want you to go home and think about. So are there two functions f and g? So find two functions f and g if such functions exist, such that you can commute these ones. Either are there two functions that f composite g is equal to 0? Are there two functions that f composite g is equal to 1? So give that some thought. Shifting. We can shift. I'm going to go very quickly now so I can give you the rest of the worksheet because you guys should have done scaling and shifting in school, yeah? Okay, so I'm just going to remind you that vertical shifts, that are shifts that go up and down, you just have to add k, or this is equivalent to adding something to y. So if I add k to f, this is going to shift the graph up. And if I add h to x, this is going to shift the graph left and right, depending on the sign. So here are vertical shifts on x squared. Plus 3 gets you up. Plus 6 gets you up even more. Nothing much to explain here. How do I shift a function left? By a units. So if I asked you to do this like in high school and I said, take this function and shift it left by 2, what would you do? Yes, miss? You'd have to put in for x plus 2. What I'm telling you is that this is actually, you've been doing function composition to do this the whole time. If you compose f with the function x minus a, what you end up getting is f of x minus a. So if you compose with this g, this is actually the left shift operator, if you want to think of it like that. All right, so you can really do everything with compositions and arithmetic. Here are the horizontal shifts, right? X minus 3 squared. So notice that I wrote it like x minus 3 squared and I didn't expand it. Right? The most preferable, in my opinion, way of giving a parabola is in its factored form. So you can really immediately figure out where it's cutting the axis. So when you're shifting stuff, I just recommend that you pick a point and you track it. Because if you can figure out where one point goes, you can figure out where the rest of the function is going, right? If you pick one point from here and it goes right, the whole thing will go right. So pick the vertex or something like that. This is not shifting, this is scaling, more mistakes. So if you put a c, whoops, in here, this is going to correspond to contracting and dilating the function depending on the value of c. That is to say, if it's a fraction or if it's big. And you can also do these reflections by doing, by taking the negation of f of x or negating x in itself. So I want you to use Desmos to investigate scaling and reflecting on this function. Just see what happens when you put in values. See it go up, see it go down, make it go left, make it go right. Try to expand it and compress it. You're going to have to do a little bit of play. Don't move yet. I still have you for like 10 more minutes. So next class, we're going to talk special functions and trigonometry. I don't like trig that much. So I'm not going to give you very much of a lecture. So tomorrow, not tomorrow, yes, tomorrow, I want to work a little bit on these worksheets that we didn't do today. And maybe I'll give you like a really short, like, I don't know how I'm supposed to teach you trig. Here is a triangle. Here's a different triangle. Here's another triangle. And this is how you look at the ratios of the sides. So maybe we'll talk a little bit about the ratios of the sides. But before you leave, I just want to read the handout with you because you're going to have to go home and do it. So this was supposed to be the handout for today. It's probably going to be the case that I'm going to lecture you a bit more than the other professor does. He really does have like half the class reserved for worksheets. So if you prefer that, you can go, you can try to switch. But in any case, so here's a problem where you're given 3 data points, and what you're supposed to do is investigate what parabola goes through these 3 points. Right, this is basically sort of an introduction to data modeling. Right, so look at these 3 points, try to get a parabola through it, and try to reflect and do all the other stuff. 1 second. Yes, miss? I assume the handouts are on Quarkus. Is that not the case? Okay, so I'll make sure this is on Quarkus and Piazza. Yes. Same question. Okay, see you tomorrow then. Okay, I'll put it up.